કેમ છો બધા? So in the last lecture, we have discussed specific heat, Cp and Cv. Cp is always greater than Cv. In the Cv, heat is utilized to increase the internal energy, while in case of Cv, heat is utilized to increase the internal energy plus work done against the external pressure. So that's why Cp is always greater than Cv. So relation of Cp, Cv in terms of F and R. So gamma is equal to 1 plus 2 by F. Cv is equal to F by 2 R or R upon gamma minus 1. Cp is equal to F by 2 plus 1 R or gamma upon gamma minus 1 into R. So as per the situation, okay, we will use the equation. So find the ratio of specific heat at constant pressure to specific heat at constant volume. It means find out gamma. Gamma Cp by Cv for NH3. So it is monoatomic, diatomic, triatomic. So it is polyatomic. Okay. So gamma, so that is equal to 1 plus 2 by F. So if F is equal to 3, then 1.67, F is equal to 5, 1.44, if F is equal to 6, then 1.33. So here F is equal to, so degree of freedom, so that is more than 6. Okay, so answer should be 1.28. Answer should be, because it is polyatomic. So for polyatomic, gamma is less than 1.28 or nearer to 1.28. For gas, R upon Cv is equal to 0.67. So this gas is made up of molecules which are diatomic, mixture of diatomic and polyatomic, monoatomic and polyatomic. So how can we decide? So for that, find out gamma. So from the gamma, we can find out whether it is diatomic, monoatomic or polyatomic. Okay. So now R upon Cv is given. So Cv is equal to R upon gamma minus 1. So gamma minus 1 is equal to R upon Cv. So R upon Cv, so that is 0.67. So gamma is equal to 1.67. So that is 1.67 means monoatomic. That is monoatomic. 40 calories of heat is needed to raise the temperature of 1 mole of an ideal monoatomic gas from 20 degree to 30 degree at constant pressure. So delta Q at constant pressure, so that is 40. The amount of heat required to raise its temperature over the same interval, it means same 20 to 30 at constant volume. So at constant volume, it means delta Q at constant volume. So find out delta QV. So that is M mu Cv delta T. So delta T, so that is 10 mu. So mu is given, so that is 1 mole. So Cv is given, Cv is not given. So find out Cv. What is given? Qp. So now Qp is equal to, so that is mu Cp delta T. So from this we can calculate Cp. Cp is equal to 40 by 10. So that is 4 joule per 10. Okay, so 40, so 40 calories. So calorie per degree centigrade. Okay, so calorie per mole Kelvin. So Cp is equal to 4. We want Cv. So Cp minus Cv is equal to R. So Cv is equal to Cp minus R. So 4 minus 2. So that is 2. So multiply. So 1 into 2 into delta T. Delta T is 10. So answer is 20 calories. Okay, so heat required for constant volume. So that is 20 calories. So now at constant volume, the specific heat of gas is 3R by 2, then value of gamma. So Cv is given, so Cv is equal to R upon gamma minus 1, and that is equal to 3R by 2. So R R cancel. So gamma minus 1 is equal to 2 by 3. So gamma is equal to 2 by 3 plus 1. So that is 5 by 3. So answer is 5 by. For a gas, the difference between two specific heat is 4150 joule per kg Kelvin. So Cp minus Cv is equal to 4150. What is the specific heat at constant volume? Find out Cv of gas if ratio of specific heat. So that is Cp by Cv is equal to 1.4. So A minus B is given, A upon B is given. Find out A or B. So very simple. Replace Cp. So Cp is equal to 1.4 Cv minus Cv is equal to 4150. So Cv is equal to 4150 divided by 0.4. Okay, so answer should be nearer to 10375. Okay, zero point 0.4 means increase by 2.5 times. So 2.5 it means 410375. So two cylinders A and B fitted with piston contains equal amount of ideal diatomic gas at 300 Kelvin. Piston A is free to move. So piston A is free to move. It means process is constant pressure process, and B is fixed. It means constant volume process. The same amount of heat is given to gas in each cylinder. Okay. If the rising temperature of gas in A is 30 Kelvin, then rise in temperature of B. So same amount of heat is given to each cylinder. It means delta Q at constant pressure is equal to delta Q at constant volume. So constant pressure mu Cp delta T at constant pressure mu Cv delta T at constant volume. So now what is given? The rise in temperature of gas A. So delta A is given. So that is 30 Kelvin. So A, so constant volume. So that is B. A means constant pressure. So delta T P is given. So mu cancel. Cp by Cv delta T at constant pressure. So that is delta T at constant volume. So Cp by Cv. So that is gamma. So gamma for diatomic gas. So gamma is equal to 1 plus 2 by F. So degree of freedom 5. 5 plus 2, 7 by 5. Cp by Cv. So that is 7 by 5 into 30. So answer is, so that is 42 Kelvin. Answer is 42 Kelvin. So specific heat of gas has only two value, Cp and Cv, not many value, has a unique value at given temperature, so that is not possible, can have any value from 0 to infinity, yes, so that already we have proved, and depends upon the mass of the gas, does not depend upon the mass of the gas. So answer is any value between 0 to infinite, may be negative value also. The specific heat at constant volume for monoatomic gas for monoatomic argon is 0.075 kilocalorie per kg Kelvin. So this is gram specific heat, where it is gram molecular specific heat Cv. So that is 2.98 calorie per mole Kelvin. So this is capital C and this one is small c. The mass of argon atom. Mass of argon atom. Okay, so find out the relation between C and C. So capital C is equal to M into small c. So capital C, so that is 2.98. Capital M, that we want to find out small c, so that is 0.075. So here unit is calorie per mole Kelvin. So here unit is kilocalorie per kg Kelvin. So here answers, here it is calorie. So here it should be calorie. So convert kilocalorie into calorie. So multiply it by 10 raised to 3. Okay, calorie per mole. So here it should be calorie per gram. So convert kg into gram. So multiply it by 10 raised to 3. So now 10 raised to 3, 10 raised to 3 cancel. So m is equal to 2.98 divided by 0.075. Okay, so this is molecular mass. Okay, we want mass of argon atom. So for one atom, what should be the mass? So m is equal to mass of one atom. Divide it by Na. Divide it by Na. So divide by Na. Na is 6.02 into 10 raised to 23. Okay, so what should be the answer? So answer should be, so here it is approximately, you can say 300. Okay, you are considered 7.5 into 6. Okay, so approximately 50 upon 7.5. So 6.6 into 10 raised to minus 23 gram. So when an ideal diatomic gas is heated at constant pressure, the fraction of heat energy supplied which increases the internal energy of gas. Okay, so at constant pressure, delta Q is equal to delta U plus delta W. So what is the question? Fraction of heat energy supplied which increases internal energy. It means find out delta U by delta Q, delta U by delta Q. So what is delta U? So that is mu Cv delta T. What is delta Q? So that is mu Cp delta T. It means Cv upon Cp. So that is 1 upon gamma. So delta U by delta Q is equal to 1 upon gamma. And ideal diatomic gas. So for diatomic gas, gamma is equal to 1 plus 2 by F. So that is 7 by 5. So answer is 5 by 7. So answer is 5 by 7. So remember this equation, delta U by delta Q. So that is 1 upon gamma. Okay, similarly, delta W by delta Q. So that is equal to, so delta U plus delta W, so that is 1. So 1 minus 1 upon gamma, 1 minus 1 upon gamma. So that is delta W by delta Q. So fraction of work, so that is 1 minus 1 upon gamma. Fraction of internal energy, 1 upon gamma. So remember these two shortcuts. Clear? So you will realize importance in the next few examples. The temperature of 5 mole of gas which has held at constant volume, so V is constant, was changed from 100 to 120 degrees centigrade. So rise in temperature, so 20 degree. The change in internal energy was found to be 80. So delta U 80 joule. The total heat capacity of gas at constant volume. So find out total heat capacity. So total heat capacity, so delta U is equal to mu Cv delta T. So this mu Cv, that is called total heat capacity. So mu Cv is equal to 80 divided by delta T. So delta T is 20. So answer is 4. So 4 joule per Kelvin. So that is total heat capacity. A gas is heated at constant pressure. The fraction of heat supplied used for external work. So already we have derived 1 minus 1 upon gamma. Fraction of work. So that is 1 minus 1 upon gamma. So now you can give the answer very easily. A monoatomic gas expands at constant pressure on heating. The percentage of heat supplied that increases the internal energy of gas and that is involved in expansion. So how much percentage is utilized in increasing internal energy and how much percentage in expansion of gas? Okay, so already we have derived. Okay, for internal energy, delta U by delta Q, so that is 1 upon gamma. Gas is monoatomic, so gamma is equal to 1 plus 2 by F, so that is 3 plus 2, 5 by 3. So your answer is 3 by 5. In terms of percentage, multiply it by 100, so you will get 60%. Okay, so 60% for internal energy, rest 40% for work done. So 60% energy will be utilized to increase the internal energy. The average degree of freedom per molecule of gas, so that is 6. So F is equal to 6. The gas performs 25 joule of work when it expands at constant pressure. Okay, so delta W at constant pressure, and that is equal to 25 joule. Then heat absorbed. Okay, so if we know delta W by delta Q, that is equal to, so that is equal to 1 minus 1 upon gamma. Okay, so from this we can calculate gamma. So gamma is equal to 1 plus 2 by F. F is equal to 6. So 1 by 3. So gamma is 4 by 3. So now use this delta W. So that is 25. Delta Q we want to find out 1 minus 1 upon, so you can say 3 by 4. So 4 minus 3, 1 by 4. So delta Q is equal to 100 joule. Delta Q is equal to 100 joule. Certain amount of an ideal gas are contained in closed vessel. So ideal gas is contained in closed vessel. The vessel is moving with a constant velocity. The vessel is moving with constant velocity. Molecular mass of the gas is m. The rise in temperature of gas when vessel is suddenly stopped. So when vessel is suddenly stopped, it means kinetic energy converts into internal energy, and because of internal energy, temperature increases. Okay, it means law of conservation of energy. Change in kinetic energy, that is equal to change in internal energy. Okay, so change in kinetic energy, so moving with velocity v. Okay, and final velocity 0, so that is 1 by 2 m v square. Delta u, so that is m cv delta t. So we want to find rise in temperature, so that is delta t. So now mu, so anywhere mu is not given. Cv, so cv is not given, so convert mu and cv. So 1 half m v square. So mu is equal to m upon m, and cv is equal to r upon gamma minus 1. So that is delta t. So m cancel. So I can say m v square gamma minus 1 upon 2r is equal to delta t. M v square gamma minus 1 upon 2r is equal to delta t. M v square gamma minus 1 upon 2. The density of polyatomic gas in standard condition is 0.795 kg per meter cube. So density is given. Specific heat of gas at constant volume. So specific heat Cv is equal to R upon gamma minus 1. Okay, but here suppose unit is calorie per gram Kelvin. So if your unit is joule per kg Kelvin, instead of capital R you have to use small r. So Cv is equal to R upon gamma minus 1. So how to find specific gas constant R? So what is given density? So use equation PV is equal to mRT. So P is equal to rho RT. R is equal to P by rho T. So here we can use R is equal to P by rho T. So P by rho T into gamma minus 1. So what is pressure? Pressure is 1 into 10 raised to 5 Newton per meter square at standard condition. Density, so that is 0.795. Temperature, standard temperature 273. Gamma, so that is 4 by 3 minus 1. Okay, so now approximate answer we can find out. So 10 raised to 5. Here I can consider zero point 0.8. So 270, or I can consider 300. Here 1.33. So for 1 by 3, so that is approximately 0.3. Okay, so you can consider 3 into 3, 9 into 8, 72. So 10 by 7. So answer should be 1400 joule per kg Kelvin. Okay, so you can see, understand the importance of unit. Okay, so here joule per kg Kelvin. So we are considering small r instead of capital R. The value of Cp minus Cv is equal to 1.00 R for gas in state A. Okay, so for state A, Cp minus Cv is equal to 1.00 R, and Cp minus Cv is equal to 1.06 R in state B. If Pa and Pb denotes the pressure and Ta and Tb denotes the temperature in the two state, then okay, so what is the comparison between Pa and Pb? Okay, so now here Cp minus Cv, so that is 1 R. It means here the gas behaves like a ideal gas. So gas behaves like a ideal gas. But here Cp minus Cv is equal to 1 point. It means gas behaves like a real gas. It means gas is real gas, but at state A, it behaves like a ideal gas. So in which condition gas behaves like an ideal gas? So at lower pressure and at higher temperature. It means at lower pressure, it means Pa should be less than Pb, and at higher temperature, it means Ta should be greater than Tb. Ta is greater than Tb. Okay, so answer is C. So at lower pressure and at higher temperature, gas behaves like an ideal. Our next process, so that is adiabatic process. So in adiabatic process, so heat transfer during the process, so that is 0. So delta Q is equal to 0. No exchange of heat takes place between it and surrounding, then process is called adiabatic process. So now you can consider piston cylinder assembly. You can consider these walls are, all these walls are insulated wall. Assume piston is also insulated. It means there is no heat transfer to the system or from the system. It means you can consider this process is adiabatic process. So assume initial position of the piston. It means pressure P1, volume V1, temperature T1. Okay, so with external work, okay, so pressure, so with pressure P2, so that is increases, volume decreases, but temperature, so temperature will change because temperature is not constant. So temperature, so that it depends upon the situation, but here temperature will also increase. How? So that we will discuss later. So now here there is a pressure, volume and temperature, all are changes, okay, but here there is no heat transfer, only the change in pressure, volume and temperature, that is due to work done on the system or work done by the system. Okay, so now you can consider the first necessary condition, the walls must be adiabatic. So first necessary condition, insulating wall. Okay, but ideally insulating wall, so that is not possible. No perfect insulation is available. So what should be the another situation? So in reality, most of the processes are rapid process. Most of the processes are rapid process. Consider the speedometer indicated by the activa, that is, so approximately speedometer is 3000 rpm. It means in 1 minute there are 3000 rpm. So in 1 second, so divide it by 60, it means 50 revolution per second. So in one revolution, piston moves from top to bottom and bottom to top. It means in one revolution there are two strokes. It means 50 revolution means there are 100 strokes of piston. Okay, so one process means one stroke. It means one in 1 second there are 100 stroke. It means time is very less. So if time period is very less, and most of the processes are actual processes are rapid process. So we can consider this actual process, so that is adiabatic process or nearer to adiabatic process. Okay, so second condition, so if process is rapid process, then again it is adiabatic process, or if all the walls are insulated, then it is adiabatic process. So all the walls of the container and the piston must be perfectly insulating or compression or allowed to expand suddenly. So this rapid process, that is also adiabatic process, but no process is perfectly adiabatic. Okay, so there is always slight transfer or small transfer of heat. Always process is not adiabatic, but process is always polytropic. Okay, so example of some adiabatic process. So sudden expansion or compression of gas or steam. Okay, sudden compression or expansion of gas or steam in the container with non-conducting walls. Okay, so second, sudden bursting of tube of bicycle tire. Okay, sudden burst. So that is again no time. It means adiabatic process. Okay, propagation of sound wave. Okay, so propagation of sound waves, that is in within fraction of second. Okay, it means process is rapid process. So propagation of sound wave in air and other gases. Okay, similarly for steam. So first law of thermodynamics. So in the first law of thermodynamics, delta Q is equal to delta U plus W. So now delta Q, so that is 0. So delta Q is 0. It means delta W is equal to minus delta U. Delta W is equal to minus delta U. So if work is done on the system, okay, or work is done by the system. If work done by the system, then delta W, so that is positive. So if delta W is positive, delta U, so that is negative. It means internal energy decreases. It means work is done at the expense of internal energy. So temperature decreases. So temperature decreases. It means process is cooling process. Process is cooling process. So you can experience this. Okay, fill the balloon with air. Fill the balloon with air. Okay, after some time, okay, just release the air. So when you release the air, there is sudden expansion. So because of sudden expansion, temperature decreases. So you will feel cool air. You will feel cooled air. Clear? So this is example of adiabatic expansion. Okay, similarly work done on the system. So when work done on the system, it means delta W negative, so delta U positive. Delta U positive, it means final internal energy is more than initial temperature, initial energy. It means final temperature is more than initial temperature. So process is heating process. So delta W negative, delta U positive. So adiabatic compression produce heating. So temperature increases. So equation of state. So equation of state represents relation between pressure, volume and temperature. So here we can derive the equation PV raised to gamma is equal to constant. Okay. So delta U plus delta W is equal to 0. For small changes you can write du plus dw is equal to 0. Okay. So du is equal to mu Cv dt. So du is equal to mu Cv dt and dw is equal to p dv. So now use it, mu Cv dt plus Pdv is equal to 0. So now replace dt. How can we replace dt? So Pv is equal to mu Rt. So Pdv plus Vdp is equal to mu R dt. So dt is equal to Pdv plus Vdv upon mu R. So replace here. So mu Cv Pdv plus Vdp upon mu R plus Pdv is equal to 0. Okay, so now mu cancels Cv by R, so that is gamma by 1. Okay, so Pdv plus Vdv upon gamma minus 1. So PdV plus VdP upon gamma minus 1 plus PdV is equal to 0. So when you simplify, you will get gamma PdV plus VdP, gamma PdV plus VdP is equal to 0. Okay, so divide it by PV. Okay, so when you divide it by PV, you will get gamma dV by V plus dP by P is equal to 0. So this is for small changes. For total changes, so integrate. Okay, so when you integrate dV upon V, 1 upon V log V, so you can see gamma log V plus log P is equal to constant. So log of V raised to gamma into P is equal to constant. Constant is equal to log of P. Okay, so you can say PV raised to gamma is equal to constant. So that is law of adiabatic process. That is law of adiabatic process. So this is relation between pressure and volume. Okay, you can find the relation between volume and temperature. So replace P. You can find the relation between pressure and temperature. So replace V. Okay, you can see TV raised to gamma minus 1 is equal to constant, where replace P is equal to mu RT by V. Okay, but no need to remember. Similarly, you can find this, no need to remember. At the end, I will give you one equation that is useful for almost all examples. Okay, next is indicator diagram. So indicator diagram is PV diagram is called indicator diagram. So for expansion process, okay, so indicator diagram, so that is hyperbola. No, PV is not equal to constant. PV raised to gamma is equal to constant. So what should be the slope of the curve? So we want to find the slope of the curve. Okay, so PV raised to gamma is equal to constant. So now differentiate. Okay, slope means dP by dV. Okay, so differentiate. So differentiation dP into V raised to gamma plus P gamma into V raised to gamma minus 1. So dP into V raised to gamma plus P gamma into V raised to gamma minus 1 dV. So now rearrange, you will get dP by dV is equal to gamma P V raised to gamma minus 1 upon V raised to gamma. Okay, so V raised to gamma minus 1, V raised to gamma, so here P by V. So slope tan phi is equal to minus gamma P by V. Tan phi is equal to minus gamma P by V. So this is slope for adiabatic process. So already we have derived slope for isothermal process and slope for isothermal process. So that is minus P by V. It means slope of adiabatic process is greater than slope of isothermal process. Slope of adiabatic curve, slope of isothermal curve, so that is equal to gamma. It means slope is greater than 1 because gamma is greater than 1. It means slope of adiabatic process is always higher than slope of isothermal process. Specific heat, so already we have derived C is equal to delta Q upon mu delta T. So delta Q 0, it means specific heat is equal to 0. So adiabatic elasticity, so what is adiabatic elasticity? What is elasticity? So when you compress the object, again it comes to its original position, that is due to elasticity. Similarly, when we compress the piston, when we release the load, piston will come to its original position. So that is due to elasticity of air. But in this process, there is no exchange of heat. Okay, so in adiabatic process, okay, so which parameter will decide the elasticity? It means piston will come back to its original position. Okay, so this adiabatic elasticity, so that is stress upon strain. It means dP upon dV by V. So now calculate PV raised to gamma is equal to constant, differentiate and rearrange. You will get gamma P is equal to dP upon minus dV by V. So this is stress upon strain. So this is called adiabatic elasticity. So that is gamma times P. Okay, for isothermal process, that is E theta is equal to only P. It means ratio of adiabatic elasticity and ratio of isothermal elasticity is again gamma. Okay, it means adiabatic process, air is more elastic compared to isothermal process. Okay, it means piston will come back to its original position immediately or at faster rate. Okay, so next is work done in adiabatic process. So in any process, work done is always integration of P dV, integrate from Vi to Vf. So W is equal to integration of P dV from Vi to Vf. Now replace P. So process P is equal to K upon V raised to gamma. So K upon V raised to gamma. Okay. So now integrate this. So integration of x raised to n. So x raised to, so V raised to gamma means V raised to minus gamma. So minus gamma plus 1 upon minus gamma plus 1. Okay. So now replace. So first V2 and then Vf and then Vi. So 1 upon gamma minus 1, 1 upon 1 minus gamma, k upon Vf raised to gamma minus 1 minus k upon Vi raised to gamma minus 1. So now replace k by, so k is equal to Pv raised to gamma. So you can say Pf Vf raised to gamma and Pi Vi raised to gamma. So I can write here Pf Vf raised to gamma and here Pi Vi raised to gamma. So Pf Vf raised to gamma and Vf raised to gamma minus 1. Okay, so here you will get Pf into Vf. Here you will get P1 Pi into Vi. So you will get equation Pf Vf minus Pi Vi upon 1 minus gamma. Now PV is equal to mu RT. So here you can write mu RTF and mu RTI. So mu R constant. So TF minus TI. So mu R TF minus TI, that is 1 minus gamma. Okay, but normally we use P1 V1 minus P2 V2 upon gamma minus 1. So P1 V1 minus P2 V2 upon gamma minus 1 or mu R TI minus TF upon gamma minus. Remember these two equation. Okay, so many times we will use this equation. Next is free expansion. Okay, so expansion means volume increases, but free, it means freely, without any restriction. Without any restriction, that is called free expansion. So consider this container, okay, which has two parts. So one part here pressure is vacuum, it means pressure is 0. In second part pressure is P and volume is 2. Okay, again walls are adiabatic, okay, and walls are rigid. So walls are rigid, walls are adiabatic. Okay, it means delta Q, so that is 0. There is no heat transfer. Okay, so now remove this partition or puncture this partition. Because of puncture, the gas will move from high pressure region to vacuum region. But is there any restriction? So there is no restriction. So this expansion is called free expansion. Okay, so gas will move from high pressure region to vacuum. Okay, so finally pressure is equally distributed among the wall. Equally distributed. Okay, so this process is called free expansion. Expansion without any restriction. So now in this process, think about the energy. So here, is there any heat transfer? No, it means delta Q 0. Okay, what about delta W work done? So work done against the piston. So there is no displacement. So there is no displacement. There is no change in volume. So total volume of the system. So our system is same. Total volume is same. So total volume is same. No change in volume. It means work done 0. So delta Q 0, delta W 0. So delta Q is equal to delta U plus delta W. It means delta U 0. It means U2 minus U1 is equal to 0. It means U2 is equal to U1 is equal to U is equal to constant. So internal energy remains constant. No change in internal energy. It means there is no change in temperature. So during free expansion process, temperature remains constant. During free expansion process, temperature remains constant. Okay, so now you can see delta U 0, so UF is equal to UR. Okay, so final and initial energies are equal. Okay, so relation between pressure, volume and temperature. So here I will give you one equation. No need to remember this equation. This already you know. Okay, so now write down this equation. P2 by P1 is equal to V1 by V2 inversely proportional raised to gamma is equal to T2 by T1 raised to gamma upon gamma minus 1. Okay, so pressure and temperature directly proportional, volume and temperature inversely proportional, pressure and volume inversely proportional. Okay, so from this you can find out relation between V1 and V2. So V1 and T1. So you can see V1 by V2 is equal to T2 by T1 raised to 1 upon gamma minus 1. So V1 by V2 is equal to T2 by T1 raised to 1 upon gamma minus 1. So you can use this equation for any example. So remember this formula, P2 by P1 is equal to V1 by V2 raised to gamma is equal to T2 by T1 raised to gamma upon gamma minus. So now comparison of isothermal and adiabatic process. So most of the time you will find example based on comparison of isothermal and adiabatic process. Okay. So now you can see process 1 to 2. So that is compression or expansion. So this process is compression process because volume decreases. So now out of process 1 and 2, which one is isothermal and which one is adiabatic? So how can we decide? So we know the rule. So thumb rule is slope of adiabatic process is more than slope of isothermal process. So in which case slope is more? So now you can see slope for process 1 and slope for process 2. So slope for process 1 is more than slope for process 2. It means process 1 should be adiabatic process and process 2 should be isothermal process because slope is less. Okay, so now you can see for isothermal process slope is less. Clear? So process 1 adiabatic process, process 2 isothermal process. So now various, so work done. So work done is minimum in which case, okay, so let me remove. So now process 1 is adiabatic, process 2 is isothermal. So area under the curve represents work done. So area of isothermal process is less than area of adiabatic process. It means work done in isothermal process is less than work done in adiabatic process. Okay, so work done of adiabatic process is greater than work done of iso. So which process is ideal process for compression? So for compression, work done on the system, so work should be minimum. It means ideal process of compression, that is isothermal process. Ideal process for compression, that is isothermal process. Okay. Now final pressure. So final pressure of adiabatic process is greater than isothermal process. Final temperature of adiabatic process is greater than isothermal process. Okay. So you can compare for compression. Similarly, we can compare the process for expansion. So you can see in expansion process 1 to 2. So process 1 and process 2. Again, identify which process is adiabatic and which process is isothermal. So slope is less. Okay, so process 1 and process 2. So here slope is more, here slope is less. It means process 1, so that is isothermal process, process 2, so that is adiabatic process. Process 2 is adiabatic process. Clear? So now you can see in the expansion process, so work of isothermal process is greater than adiabatic process. So in expansion process, generally we get the work. Okay, so for more efficiency or for ideal process, work should be maximum. It means isothermal process is again ideal process for expansion. So isothermal is ideal process for compression as well as expansion. Okay, so work of isothermal process is greater than work of adiabatic process. Okay, now final process in final pressure. So final pressure of isothermal process is greater than adiabatic process. Final temperature of isothermal process is less than adiabatic process. So in adiabatic process, so there is more cooling. Adiabatic process, there is more cooling. Okay. So now in the next lecture, we will solve example based on adiabatic process. So thank you very much.